Hello again. So just before starting the talk, I actually have a teaser. Oh, I don't have it. I don't have the sound. That's too bad.
It's not going to do the HDMI.
Well, you know the sound. Somebody wants to sing the theme?
Secretly modified.
Secretly. Okay, thank you. Sorry. So let's be serious for just a couple of seconds. So, why methods combination are a good thing? So in C++, for instance, if you're executing the code of one method and you need to reuse the code of another one, you have to write something like class : method to call the next one. In Java, you have a slightly more abstract way of doing it, which is calling super.method. It's slightly more abstract because you don't need to know implementation details such as the name of the other class. Otherwise, you would have to modify every call site in case the hierarchy changes. In Lisp, we have call next method, which is more or less the same kind of idea. It's even slightly more abstract than calling super.method because on top of calling a method for which you don't necessarily know the structure of the hierarchy by name, you also have a complete reification of all the applicable methods and sorted by decreasing specificity order. So this is nice, but this is not from a software engineering point of view. This is not completely satisfactory because when you do things like that, you are essentially mixing up two different things. You have the job of each method, and every time you need to call another method, you're essentially doing a form of dispatch. And that's just because the default dispatch mechanism implemented in the language is not completely satisfactory. Then you have to do some form of ad hoc dispatch on top of the existing one. So this is not really nice because you end up doing two different things which in an ideal world should be separated completely. The job of the methods themselves and then the way the methods are organized and the different calls are organized sequentially. Okay? So method combinations are a good thing for that because if you do something like this as in CDOS, the code within the methods themselves is really just related to what the methods actually need to do. And not only the dispatch mechanism implementation is completely separated from the method implementations themselves, but on top of that, you have a declarative way of specifying the kind of dispatch that you want, rather than calling call next method or any other kind of facility, which is actually imperative. Okay, so these are the two main advantages of method combinations. And to sum things up, it just means that when you have that, you have increased the level of orthogonality in the language or separation of concerns. What is the benefit of a meta-object protocol? So a meta-object protocol essentially exposes the implementation of a language, which can be useful for two different things, introspection and intercession. And how it does that, for instance, in the common Lisp MOP, you have a set of standard classes which are available for subclassing or even modification if you want. You have a set of standard generic functions which are available for specialization on the new classes or even modification if you have the ability to remove existing methods, for instance. So all of this is very well, and in the case of the CLOS MOP, for instance, it provides you with what's called homogeneous behavioral reflection. This is a pompous expression, just mean that homogeneous, it's because the MOP and the language you're modifying is the same one. Behavioral, it's because you have the ability to modify the semantics of the language itself, and not only the semantics of the program which is executing. And reflection, because you have both introspection and intercession. So all of this is very nice, except for one thing. If you look at the Common Lisp standard, you have, when it comes to method combinations, you have one class method combination in the specification. It's supposed to be abstract, and that's basically all there is to it. And then you have one macro, defined method combination, and that's it, okay? So as a result, this lack of specification entails a number of consequences, a number of problems. So for instance, you cannot hope to write any kind of portable code related to method combinations because of the lack of specification. Would it be only for one basic reason, which is that you necessarily need at least one implementation specific class for them, because the method combination upper class is supposed to be abstract. There is a number of ill-designed protocols in the specification. Some of them that we would have liked to have, for instance, are also missing. Two examples are find method combination. If I remember correctly, find method combination is even specifically not implemented in LispWorks, I think, because it's ill-defined. Compute effective method is a bit weird also. The way you're supposed to implement method combination is unclear. Are they supposed to be classes? Are they supposed to be instances of classes? We don't really know. And on top of that, the implementation, that's about the nature, but the implementation also is subject to a number of potential confusion. For instance, this is an extract from the CLHS part about the method combination class, which is supposed to be abstract. It says that it contains information about both the type of the method combination in use and the arguments of the generic function calling that particular method combination. So you have almost an explicit mixture of different things, which are the define time options to define method combination, but also the call time or use time options that generic functions are going to use, okay? Did I mention separation of concern already? Well, so there you have it. Or actually, you don't have it. So I'm not going to talk anymore about those problems, because that was essentially the purpose of the 2018 paper to ELS. What I'm going to do in this talk is propose a MOP-based implementation for method combinations. So I'm not talking about their usage, I'm talking about their implementation. And this design that I'm proposing here has the virtue of being standard compliant, also portable. So I'm hoping that as many Lisp vendors would adopt it eventually. And I'm ready to, pay some checks. We'll see. So here's the overview of the design that I'm proposing. And actually also the idea that I would like to convey is that generally when you enter the world of meta-circularity and meta-object protocols and all that stuff, things can be a bit scary. Okay, reflection is both fascinating and frightening. But if you manage to formulate the problem in the appropriate terms, then I also think that it's not scary anymore, and the solutions can be quite natural. So I would like to convey the feeling that maybe the difficult thing is not to find solutions, but to formulate the questions in the most appropriate fashion. So point number one, if you read the standard consistently speaks of method combination types, okay? But we're evolving in the object-oriented world. And so we have this pseudo and admittedly somewhat shaky equivalence between types and classes. So there is here a strong incentive that method combinations should be reified as classes of some kinds, okay? So that's the first thing. And maybe generic functions using method combinations should actually instantiate those classes, as opposed to, I don't know what. Point number two, as you all know probably, there are two forms of method combinations, because the macro define method combination comes in two flavors, the short form and the long one. So it means that maybe method combination forms should also reified as some kind of types or classes, okay? So in the end, it would mean that we have two classes of method combinations. And this is how you naturally enter the world of meta objects, in fact. And so it is not so complicated after all. So if you want to formulate the things properly and sum things up, we could say that a method combination class is a short or a long one. And there we're talking about the is-a relationship, which in object orientation means the inheritance relationship. But at the same time, a method combination is of the short or of the long kind. And so there we're talking about the implementation of the method combination classes. So in other words, we have classes of method combinations. Okay, so this is the general idea. So it means that what we're going to have is two different hierarchies, one for regular method combinations and one for their implementation. Here is the regular method combinations hierarchy. So this one is extremely close. It's practically the same one as the original PCL1, and it's not so different from the SBCL and the CMU-CL1, for instance. So you have the method combination class at the top level, which is the only one which is standardized in Common Lisp. Then you have standard method combination, and I would like to draw your attention here to the fact that this is not the standard method combination. This is confusing, but the standard method combination in the Common Lisp standard is one particular method combination. In the rest of CLOS, you have standard method, you have standard generic function, you have standard class, you have standard object, and this aims at playing the same role. You always have one upper level class, one standard blah blah blah, which is the base for implementation of everything else. So standard method combination here is not the same as the standard method combination object in CLOS, okay? Big warning here. And then you have a class for short method combinations and a class for long method combinations, okay? The only common thing in this hierarchy is the option slot, and the option slot is available for every kind of method combination because it will be used to store the actual options used at runtime by a generic function when it uses a specific method combination. So that's the basic hierarchy. It's not complicated at all for method combination objects, okay? Now, how do we want to implement method combination themselves? So classes of method combination. So the idea is not complicated either. We have, and that is actually the new hierarchy, which doesn't exist at all in any implementation or even less so in the standard. So we have a base class for every kind of method combination. So this is going to be called method combination type, as in the standard. You have standard method combination type, which also plays the equivalent role as standard object, standard class, and all that stuff. Something common to every method combination class or type is the name and the lambda list. Yes, there is a lambda list also for the standard method combination object, but this lambda list happens to just be nil. That's all, but this is still a lambda list. And then you have a subclass for the short method combination types, and then you have a class for the long ones, okay? In the short method combination type, you have two specific slots which describe the method combination type as defined by defined method combination. And so the short form has an operator and another option, which is the identity with one argument that you probably all know, okay? So we have those two different hierarchies. The first one is for regular method combinations, and this one is for their implementation. So these are the meta classes. How do these hierarchies now work together? So let's look at a couple of examples. Suppose that I want to define the standard method combination as the Common Lisp standard defines it. So standard method combination is a name that I've used for something else. So to remain coherent, this one should be called standard method combination. I love, whatever. So if you come up with a better name, Be my guest. But this one I think is nice. Okay, it's explicit, and if you understand how it works, there is no ambiguity. So we have the base class, which is standard method combination. Every method combination class is going to be a subclass of this one. So we're going to have a standard method combination class for the standard method combination from the Common Lisp standard, which happens to be a singleton class as well, because there is only one instance of that class, the standard method combination. But this standard method combination class is going to be implemented as a standard method combination type. Do you follow me? Yeah. So in the implementation class, in the meta class that I'm using here, we have a type name and a lambda list options. So the type name obviously is standard, and as I said, the lambda list is nil because the standard method combination doesn't have any option. Okay. If you create the only instance of that class, because again it's supposed to be a singleton, then you have an option slot, but this option slot is provided by the standard method combination class upwards in the hierarchy. And the value of this slot is also nil because we never pass any options to the standard method combination. Okay? Simple enough. So the regular hierarchy and another hierarchy, again, for implementation of the classes. Okay, so the meta hierarchy, if you will. Let's just look at another example, short method combination. Suppose you want to define, say, the progen short method combination, okay? So we have, again, standard method combination at the top level. You have a subclass for all short method combinations, which is called short method combination. This is not so different from the PCL, again, implementation. All I did basically on that hierarchy is move a number of slots around, but that's basically it. Now we want to define, we call define method combination on progen, for instance, to define the short form of the progen method combination. So this will create a new class, which prefers to remain anonymous. I don't want to pollute the global class namespace with method combination classes because they are generated automatically by the system. So I have a tendency to consider those as part of the implementation. So they're not supposed to be public. That's why it remains anonymous. But this class is supposed to be implemented as a short method combination type. Okay? So the implementation of the class itself is going to be from the short method combination type kind. Okay? So we have a number of slots here. In short method combination type, we have type name and lambda list. In the case of the progen method combination, it's a short one, so the type name is progen, and the lambda list is the same lambda list that you have for all short form method combinations. Okay, so you have this optional order argument. In the short method combination type meta class, you have the operator slot, which is going to be filled up with the name of the corresponding Lisp operator, which happens also to be progen. And you have the identity with one argument option, the default value of which is t. Okay. So again, the hierarchy for using the method combinations and the hierarchy for implementing the method combination classes. Now, what we can do is use that method combination class by defining generic functions which are going to use it, maybe passing a number of options to that. So if I have a generic function which happens to use the method combination called progen without any options, we're going to instantiate that anonymous class, and then we have the options slot which is provided upward in the hierarchy and which is going to be nil. But there is also another possibility, which is to use the progen method combination passing the order argument. So the generic function would do something like colon method combination progen t, for instance, or most specific last, for instance. So if you do that, you will end up with a new instance, a second instance of the anonymous class, and this time the option slot will contain the call time options as used by the call to def generic. Make sense? Simple enough, actually. Okay. So basically that's it. That's the two hierarchies, and there is nothing so complicated about that. Apart maybe from the standard stuff, whatever. Okay, so I have an implementation for this because remember the fork is with me. So I have implemented that in an SBCL fork, and the implementation is actually pretty straightforward, apart from just one thing, which is the bootstrap phase. Bootstrapping CDOS, as you know, is something quite even scarier than meta-circularity and everything. And I'm scared by the bootstrap of PCL. I don't really know how that works, so I dug into that a little bit. And what I eventually figured that is that there is actually a not so complicated way to bootstrap this whole thing, because the complete infrastructure with the meta classes cannot be implemented at bootstrap time. But as it turns out, in SBCL, there are only two method combinations used during the bootstrap. There is the standard one, obviously, which is needed for most of the generic functions out there. And there is also another one, which is the OR short method combination. And oddly enough, it's used for a single generic function during bootstrap. But we still need those. And in the bootstrap code in SBCL, those two method combinations are used like all over the place. So I didn't want to touch that code too much. So what I did was actually something which is also quite simple. I have re-implemented specific method combination classes for just these two early ones by reintroducing the slots that I've moved around in the original hierarchy. So what I have is an early short method combination class, and as you can see, the slots in that class are the ones that have been moved from the normal hierarchy to the implementation, to the meta hierarchy, if you want. And there is also an early standard method combination class, which gets back the type name option, which belonged to the original PCL implementation, but again, which has been moved to the meta class hierarchy. Okay. So instead of instantiating the former short method combination and standard method combination types, the two method combination types used in the bootstrap phase of SBCL now are instances of the early classes, and that's all. Okay, so the bootstrap phase works correctly, and after the bootstrap, then you can implement the complete infrastructure with the meta classes hierarchy, and then it's actually quite simple to grab those two early method combinations, look at the generic functions which are using them, and convert them to the new infrastructure. It's just a matter of updating a couple of slots in the generic functions implementations, and also the dependency lists in the method combination objects. Okay, so actually it's also pretty simple and pretty straightforward to do. And with that kind of scheme, the amount of code that needs to be changed in the PCL bootstrap is actually quite minimal. Okay, it's just like 10 lines of code, not more than that. Okay. While we're at it, we can add a number of protocols to like improve the situation, again as described in the 2018 paper. So I'm adding a new protocol called find method combination type. The meaning of it should be quite obvious. It's the equivalent of find class, but for method combination types. As I said, the classes remain anonymous because they belong to the implementation. So they are stored somewhere in a global variable, and you can retrieve them with that. This is really the equivalent of find class, but for method combination classes. And there is also some kind of a fix-up, which I already proposed in the 2018 paper, a fix-up for the find method combination protocol, which is ill-defined in the meta-object protocol standard. So it's called find method combination star, and it does the obvious thing, which is to find a particular method combination object for a specific method combination type accessed by name and with a number of options. It really functions in the same kind of way as the original protocol, except that the find method combination protocol also accepts a generic function argument which is unused, and so this was also the opportunity to fix that. And that's it. With these two new protocols, everything works perfectly. So now let's get back to the original point. What's the purpose of this, apart from, as we said already, yes, it's an academic exercise, but do you actually have practical applications, apart from the fact that I'm a complete maniac and I like things to be implemented cleanly? Well, as I said at the beginning, the whole idea of having a meta-object protocol implementation for stuff is to be able to experiment, to prototype rapidly, and to modify the semantics of the language without having to dig into the internals and modify proprietary code or hidden or private code, because you can just extend the system rather than modify its inner implementation. So the obvious way that we can experiment with method combinations now is by subclassing the two hierarchies that we provided. So you can create subclasses in the original hierarchy. You can also create subclasses in the metaclasses hierarchy, and maybe specialize generic functions like, for instance, compute effective methods, which is one of the most interesting thing that to be experimented on. And how can we do that? Well, actually, there is a simple way of doing so, which remains standard compliant. We can take define method combination, which is the original macro in the Lisp standard, and we can provide two new options: one for specifying the class for the method combinations, and one for specifying the meta class for the method combination classes. Okay, and provided that you pass these options on late in the call to define method combination, this actually remains standard compliant, because you're not modifying in any way the behavior of the original macro if you hadn't passed the argument. The syntax is not modified and everything. So this remains standard compliant. In the long form, the syntax is slightly different, but that's essentially all there is to it. You don't need to define any new protocol for doing so. Just adding those options to the macro is sufficient to be able to experiment with it. Okay. Let's look at probably a quite silly example, but a very simple one for demonstration purposes. Suppose that I want to create a new kind of method combination, which is very frequent to do, which I call here medium combinations, which essentially is the short ones, but implemented as long ones with before and after methods re-implemented, and perhaps without the need to restate the method combination name in the method definition, because that's annoying, right? Yeah. Okay, so if you want to do that with that new, of course you can do it with a traditional long method combination. So maybe it's a bit silly to do it like this, but I, for one, with Declet, for instance, would very much like to have something like that. Would it be only for documentation purposes? Okay, and it's admittedly a simple example. So I want to recreate short method combinations, but implemented in the long form. What you can do is create a subclass long method combination, put back in there the arguments that normally belong to the short method combination family, so operator and identity with one argument. Okay, so this is your new class. You can maybe provide a new macro, define medium method combination type. You can create a myprogn method combination, which behaves like an extension of an extended version of the short one implemented as long one. So this call actually looks like the short form call to define method combination, and that could simply expand to this. And here, as you can see, you have an expansion of the long form of define method combination, but just at the end of the arguments list, you have the method combination type class option, which gets the new meta class that you've just defined, with the operator being progn and with the identity with one argument defaulting to T. And that's it. Okay, and now Declet is happy because it can grab this, get the list of the slots, and properly document that as a short long or a long short method, or whatever you want to call it. Okay, or medium. Okay, simple enough. Well, that's essentially all there is to it. I don't know how it. Oh, for the first time ever in my whole life, I'm quite on time. So just a word about the performance of this. So out of curiosity, I have roughly benchmarked. Essentially, this is benchmarks for calling compute effective method multiple times, so a gazillion times. The leftmost bars represent the original SBCL version, and the rightmost ones represent my forked version with the complete new infrastructure. So if you look at this, you see that there is a degradation of performance for the short form, but on the other hand, my system is actually more efficient on the long form of defined method combination. This is easily explained. This is just because I moved around some slots in the implementations, and in the short form, it takes longer to access some of the slots, essentially because original slots belonging to the method combination hierarchy have been moved to the meta classes hierarchy. So you need to access the meta class first and then the slot afterwards. But on the other hand, and this one is specific to the current SBCL implementation, accessing the long form method combination slots is faster in my system because they belong to the class, to the meta classes themselves. In the current implementation in SBCL, there's a couple of global variables lurking around with hash tables pointing to values which normally should belong to the meta class, or could be colon allocation, colon class slots in if you were to retain them in the original hierarchies. Honestly, I don't think performance matters much in that situation because this is essentially the performance of compute effective method. And because of all the caching that is going on, compute effective method is not likely to be called very frequently. Okay, I'd like to be proven wrong, but I don't think it matters much. But just out of a concern for completeness, I thought I would just benchmark that stuff. Okay? So to conclude, what I have here is that we have method combination types, so the meta classes, which are completely reified in that system. Originally, they don't exist anywhere in any implementation that I know of. It remains standard compliant, which is a pretty good thing, I think. It's also close to PCL's original design because the original PCL hierarchy is practically not modified, apart from a couple of slots that I've moved around. It also brings portable MOP-based extensibility to method combination. So now we have a way to portably and actually in a simple way experiment with method combination, extend those, modify those, so play with those. The SBCL fork and a more complete set of examples that of what you can do with that, which is also a follow-up to my 2018 paper, is also available on GitHub there. And there is also a lot more details in the paper, notably a couple of concerns about the SBCL specific implementation, but that's all in the paper. Thank you very much. Oh. Yes.
Say something about the relationship between our method combination templates and your method combination types. You remember from our ELS paper a few years ago?
Please repeat the question.
Yeah, the question is any relation with method combination templates and this work. Actually, no, I don't remember enough about this paper, so I cannot comment on that. Sorry.
Another question?
Thanks for the super interesting work. Will there be some kind of because you propose this as kind of standard, I guess that should be adopted would be the idea.
It's my hope that it would be adopted by many in this implementation.
Have you thought about a forum where one could discuss the protocol and the functionings just at more than one pair of eyes as when they do it?
Yes. So the question is, did I think about a forum where this could be discussed? And my answer is coffee breaks. Maybe this one. In my experience, if you want stuff to move, it's a good thing to start by writing a paper for this conference, which is what I did. Yeah.
Just about the performance, that was about
compute effective method. Yeah.
The methods remain the same.
Yes, I didn't touch that. Yes, in SBCL, for instance, there is a single implementation of of the effective method and results for all short method combinations, which is parameterized with the different options that you can pass to short forms. And there is also a generator for what's called a method combination function. And there, every method combination function is specific to a long form method combination. So I didn't touch that. But maybe this is a place where there is room for more experimentation with that system, because potentially what you could do is subclass the original hierarchy to create method combination kinds which would be neither short nor long. And then maybe there is room for implementing different kinds of optimization for the computation of the effective methods. This is one potential area of experimentation, which now could be done in a portable way, or at least in a properly defined way.
Okay.
Follow-up of that. Would it be good to I remember there is a method in the NetObject protocol which returns a lambda, which has no context about the lexical context,
Which returns a lambda.
or makes a lambda.
Make method lambda?
Oh, make method lambda.
Could
Yeah.
it be made to be inspectable, debuggable, introspectable?
I'll get back to you on this later on. I don't know the answer to that question just yet. But yeah, this is an interesting question. So sorry, the question was, is there a way to put make method lambda back into that? So yeah, I don't know.
We solved that one too.
We
solved that problem too in ELS a few years ago.
Okay, I have to get back to this then. Yeah.
Okay, so thank you, Didier.
Thanks.